Oh, welcome everyone. We are ready to finish chapter 18, the textbook part of it. You have homework that was assigned yesterday that you're supposed to be correcting today. That means tomorrow, which is Friday, you should have a review and a test next. Well, normally it would be Tuesday, so I think we'll probably plan on that. Maybe I'll give you two reviews or give you the review. We'll figure that out before then. But anyway, that's kind of where we're going. So, first question you had was 26. Two charges separated by a distance r exert a force 1 Newton on each other. If one charge is tripled without anything else being changed, what force will the charges exert on each other? And the answer is that the new force will be 3 times the old force. And I just realized the book just left it like that the new force is 3 times the old force because the charge is tripled, the force will be tripled. But since they actually told us the force was 1 Newton, that would be 3 newtons. So if you have 3 newtons, that's actually a correct answer. The book left it in abstract form, but 3 newtons is a correct answer. Okay, number 27 is kind of a cool problem, very theoretical, but just kind of a fun one, I think. So we've got a liter of water, 1,000 grams, and that contains 55.5 moles of water molecules. And they tell us that a mole is 6.022 times 10 to the 23rd particles. We sang that back last year during physical science. But anyway, and chemistry. But anyway, so that's the first step is determining, well, that's what they give us. We're going to have to determine how many molecules of water there are in part A. One electron is removed from every 100th water molecule and placed in a container 100 meters from the water. This is obviously a very theoretical problem. You couldn't actually do that. Okay, 27A. How many water molecules are there in the water container? So you have 55.5 moles. They tell us there are 6.022 times 10 to the 23rd molecules per mole. So this is basically a unit conversion, which gives us 3.34 times 10 to the 25th molecules. So that's how many water molecules there are. Letter B, how many electrons have been removed from the sample of water? And you go back to the problem, and it says 1 electron is removed from every 100th water molecule. So take the number of molecules, then we take 1 electron out of every 100 molecules, because it's 1 electron per 100th molecule. They count 100. This is like decimating a Roman legion, only it's one every 100 instead of every 10. And you take 1 electron from every 100 molecules. So you're going to actually be taking off 3.34 times 10 to the 23rd electrons. And again, this is totally theoretical. You couldn't do that. That's okay. Okay, so what is the charge then in coulombs of the electrons that were removed? Now, if you go back to page 424, they tell us that a coulomb is the charge of 6.24 times 10 to the 8th electrons. So we have 3.34 times 10 to the 23rd electrons, and 1 coulomb per 6.24 times 10 to the 18th electrons is 5.36 times 10 to the 4th coulombs. Just for the record, that is a huge charge. That is a huge charge. We're going to be dealing, the rest of the problems deal with 10 to the negative 5th and 10 to the negative 6th coulombs. So that's a very large charge. But that's okay. The last question is, what is the force of attraction between the container of water and the container of electrons? Now, the container of electrons has a charge of 5.36 times 10 to the 4th coulombs. That would be negative because they're electrons. The water is going to have a positive charge of 5.36 times 10 to the 4th coulombs because the water molecules were neutral. You pull electrons off, you don't take the protons off. It's going to have a positive charge of 5.36 times 10 to the 4th coulombs because you've taken electrons away. And so this is plug and chug into Coulomb's law. So the force equals K, Q1, Q2 divided by R squared. So I left off the absolute value signs for my convenience. Theoretically, they should be there. So 8.99 times 10 to the 9th, that's K. Both the water and the electrons have a force, a charge, of 5.36 times 10 to the 4th coulombs. And then we divide that by the distance between them. We go back to the problem, and it tells us that they are 100 meters apart. And I didn't put a decimal point on there, but that is 3 sig digs. Square that, however. And if you punch that through your calculator, you should have gotten 2.58 times 10 to the 15th newtons. And my answer key points out that that is 3 billion tons of force. So that's an unbelievable amount of force. And the reason, even though 100 meters, that's a football field. So this 2 containers are a football field apart, but because they are so charged, that is a huge charge. You've got 3 billion tons of force pulling the water container and the electron container towards each other. You don't want to be between them. Okay, let's go on to number 28. 2 conducting spheres, when given a charge of 2.50 times 10 to the negative 6 coulombs each, repel each other with a force of 2.5 times 10 to the negative 4th newtons at a certain distance. How far apart are they? So we're going to start with our basic equation, F equals K Q1 Q2 over R squared. Substitute the numbers. 2.5 times 10 to the negative 4th newtons is the force. 8.99 times 10 to the 9th is K. The 2 charges, 2.5 times 10 to the negative 6th, and divided by R squared. Do a little bit of algebra, and you should have rearranged that so that R squared equals 8.99 times 10 to the 9th times 2.5 times 10 to the negative 6th times 2.5 times 10 to the negative 6th divided by 2.5 times 10 to the negative 4th. And if you run that through, take the square root, you should get a radius or a distance between the centers of 15 meters. Okay, so it's plug, do some, and plug and chug. Plug it in, do some algebra to rearrange it, run it through your calculator, and you should get a correct answer. Some of these are, these 2 problems are very straightforward. The last one is almost as straightforward. We'll get to that in a minute. Okay, so 29, they are asking us the charge tips of 2 test rods are suspended 10 centimeters from each other. One rod has a charge of 2.5 times 10 to the negative 5th coulombs. The rods attract each other with a force of 5 newtons. What is the charge on the other rod? And this is probably a fairly realistic problem. So we plug in the numbers that we are told. 5 newtons. 8.99 times 10 to the 9th is our K. 2.5 times 10 to the negative 5th is the 1 charge. Q is the unknown charge. And the distance between them is 0.10 meters squared. Now you'll notice I changed it from centimeters to meters because they gave it to us in centimeters, but the K is in meters. And I haven't been putting units on K, which I should be. But anyway, it is in meters, so you have to make sure you change that to meters. Do the algebra to rearrange it, and you get 5 newtons times 0.1 meters squared divided by 8.99 times 10 to the 9th and 2.5 times 10 to the negative 5th coulombs. And you run that through your calculator, and you get Q, 2.22 times 10 to the negative 7th coulombs. Again, it's just plug and chug. A little bit of algebra in the chugging, but these really aren't that difficult of problems. I suppose the biggest thing is knowing what to plug in where. The Q's are always charges in coulombs. The distance, of course, is the radius, is in meters, and forces are in newtons, and K is your constant. So this is just looking at how much force there are between 2 charges. Now this one has 3 charges, A, B, and C, with A being a negative 2 times 10 to the negative 6th, and there's a 5 centimeters between it and B. B is 1 times 10 to the negative 6 coulombs, and then 10 centimeters over there's a C sphere, and that one is 3 times 10 to the negative 6 coulombs. You'll notice that A is negative and B and C are both positive. We haven't worried about the signs a lot. We're going to have to in this one. Okay, so the force between A and B, Coulomb's law, K, Q1, Q2 over R squared. Plug in the numbers that we were given. 8.99 times 10 to the 9th is our K again. Negative 2.00 times 10 to the negative 6 coulombs times 1.0 times 10 to the negative 6 coulombs divided by 0.05 meters squared. Again, centimeters to meters, you have to make sure you do that. Run that through your calculator and you get 7.19 newtons. We need to clarify, because of this problem, we do need to clarify this is going to be attractive. One was negative, one was positive, so it's attractive. We don't really follow the signs here because remember they had absolute values in the original problem, or in the original equation, but we do keep track of this. We notice that one's negative, one's positive, opposites attract, So it's an attractive force. Okay, letter B is finding the force between B and C. Same formula, K Q1 Q2 over R squared. Plug in the numbers. 8.99 times 10 to the ninth is K. The different 1.0 times 10 to the negative 6 coulombs is B. 3.0 times 10 to the negative 6 coulombs is C. And these are 0.100 meters squared apart. And if you run that through your calculator, you're going to get the force between B and C being 2.70 newtons, and that's repulsive because they're both positive. And again, with absolute value signs, that's not going to affect the sign per se, but we need to know that fact that it is repulsive. Because in letter C, they ask us what is the total force on sphere B. So let's look at that. Okay, to do C, we look at the fact that the force between A and B is 7.19 newtons, and that's toward A because it was attractive. Force BC is 2.70 newtons away from C because it was repulsive. Now, if you're looking at that diagram, if it's being pulled towards A and away from C, and being pushed away from C, you could say, then those are both going the same direction. Both forces are moving it away from C and toward A, so we add them together and we get 9.89 newtons to the left. That's the total force on B. Of course, forces are normally vectors, so left and right are very appropriate. And in this context, we definitely have to keep track of those directions. That was the homework, and hopefully that went smoothly for you. And tomorrow, then, you'll be looking at a review, beginning to do a few more of these. Well, I hope you all have a good day, and we'll talk again tomorrow.